Previously on Dr. Zai.
197 flags. You can use both PowerPoint and Google Slides. 45, 88, 94 flags, 108 flags complete.
Let's draw the flag of UK in Google Slides. First, draw a tiny unit square. We will call this length 1. We will copy it lots of times and snap them together. This enables us to create any natural number. That was theorem number 1 in our previous video. Let's make a rectangle 60 wide and 30 tall. That's how large the flag will be. For our next step, we need 4 ingredients. A white rectangle 10 wide and 30 tall. A white rectangle 60 wide and 10 tall. A red rectangle 6 wide 30 tall. And a red rectangle 60 wide 6 tall. And that gives us the cross of St. George. This is where we got stuck last time. For the next step, we needed to draw right triangles whose lengths differ by a multiple of root 5 while following the basic principles of mathematical construction. Number 1, perfect tools. Number 2, no eyeballing. Number 3, no measuring. Without further ado, here's how we make root 5. Chapter 7. Reach for the stars. There is a 5-point star in Google Slides which hides a gem called the golden ratio. Get it? Gem?
Gold is usually not called a gem, but...
The ratio between the lengths of these two segments is the golden ratio, which we can prove like this. Let's call the lengths 1 and x respectively. The symmetry of the star allows us to do this. We get two similar triangles. This means that the proportion between x and 1 is the same with the proportion between 1 and x minus 1. Solve that and you get x equals 1 plus root 5 over 2, which is called the golden ratio. Once we learn that, we can create a root 5 square like this. Draw a 5-point star as long as a unit square. That means this length is 1 over the golden ratio. I've already calculated that, which is root 5 minus 1 over 2. We snap a line to that length and draw a square as long as that. After that, we double that and add 1, and boom, that is root 5. Once we get root 5, the rest of the flag of the UK becomes very doable, just a bit repetitive. Here's a time lapse. And that's the Union Jack complete. Last time we mentioned that there are like 50 flags that require root 5, so does this mean that we can add 50 more flags to our list of constructible flags?
Well, not so fast. There are some delicacies to clear up. First off, explain why you are on Google Slides this time.
That is because PowerPoint has a very cursed feature. When you hold Shift and draw a 5-point star in PowerPoint, it's actually not a perfect star. Let's compare it with a square. Look how the star fits perfectly inside this square. This is not what should happen. In Google Slides, the star is shorter than the square. This is what should happen. The width of the star is the same as this diagonal, so that can never be as tall as this square. You can see how cursed it is when you rotate the star. First, this is how a star should look like when we rotate it. When we overlap the rotated star with the original star, it should perfectly line up. Conversely, on PowerPoint, rotate once. What? Rotate again. What? What is this? Look how deformed it is. It's so cursed. However, this doesn't mean the star is completely useless on PowerPoint because the horizontal lengths of the star are still the same. It's just stretched vertically. So this length is still 1 over the golden ratio, so the UK flag is still constructible even if you only have PowerPoint. But unfortunately, for every flag that requires a regular 5-point star, PowerPoint is not suited for the task.
Is it really impossible? What if the height of the star is a constructible number?
The height? Oh, I get what you're saying. If we can calculate how tall the star is and just make that number in PowerPoint, then we can manually resize the star into a regular star without the help of Google Slides. Okay, how tall should the star be? Like some multiple of root 5?
Well, if a star's width is 1, then its height should be the square root of 10 plus 2 root 5 over 4.
What? Okay, can you simplify that a bit?
This is already simplified.
What? Why is it that complicated?
Sometimes things are just complicated, such as life.
Okay, I can't even begin to think about how to make that number. I'll just give up for now and use Google Slides, okay? Wait, this is Editing's Eye, and the pentagon shape in PowerPoint is actually a regular pentagon unlike the 5-point star. Don't know why, but that means we can resize a star into a regular star without the help of Google Slides. But in this chapter, I'm going to use Google Slides, and it's not going to matter in the end. So, a quick review on what we can draw on Google Slides. We can do any ambiguous drawings, rectangles, circles, right triangles, and now 5-point stars, whose lengths can be built with the 4 operations, and rational numbers, root 2, root 3, root 5, and this number. I'm not even going to think about that number right now. Basically, we should be able to draw all flags with stars, right?
There's still one subtle problem. Check this construction sheet of Somalia. Can you draw this with the knowledge we have right now?
Oh, the star is not defined with a width or a height. It's defined with the diameter of its circumcircle?
That is how most stars are defined in construction sheets.
Okay, now the situation is different. We are drawing a circle first and then fitting a star inside it. So, it's obviously not as simple as making the star as wide as the circle because it's going to poke out. And we can't do any eyeballing. So, is this constructible?
You're asking us?
Right. Okay, I found a way to make the star and it actually looks like magic. Step 1, have a star as wide as the circle. Step 2, draw a square as tall as the star. So the star should be poking out from the square a little. Step 3, resize the star so it is as wide as the square. And that's it. Move the star back onto the circle and it's suddenly perfect. Magic!
Okay, so why does it work?
Let me explain. In the beginning, we have a star as wide as the circle. And the star we need to make is this gold star.
Right? Basically, you need to make the width of the star.
Yes, I'll call that length the target. Now, our current star is this wide and this tall. The length of this diagonal is the same as the width. Now remember that right triangle. It has an angle half as big as the point of the star. Now look at this right triangle. That also has an angle half as big as the point of this star, right?
Yes, so that's a similar right triangle?
Same ratio between green and red. Look closer now. The red line is the radius of the circle, and the green line is half of the width of the star we need to make. Which means, if we double the size of that triangle, then the red line will be the diameter of the circle, and the green line will be the width of the star we need to make, the target. Wait, but look left again. The width of our current star is the diameter of the circle. So the height of our current star is equal to the target. This height is equal to the width of the star we need to make. So that is why we used a square. If we turn the height of this star into the width of a new star, then we are just done. The result would be the same if we turned the original star by 90 degrees and drew a new star as wide as that. I just thought the square felt more magical. Anyway, now we know the size and positioning of these kinds of inscribed stars are constructible too. And with this, we can clear a lot of new flags. A real lot of flags.
You know what that means? It's time for another montage.
Okay, do we have something a bit more funky?
Of course, bring the piano.
Bosnia and Herzegovina, Burkina Faso, Cameroon, Central African Republic, Chile, Comoros. We are using twice as much time for these harder flags. Cuba, Fiji, Ghana, Grenada, Guinea-Bissau, Jamaica.
Time to get funkier.
Kosovo. What? Liberia. Micronesia. Mozambique. Myanmar. North Korea. Panama. Samoa. Senegal. São Tomé and Príncipe. Solomon Islands. Somalia. South Sudan. Suriname, Syria, Togo. Interesting fact, one popular version of this has the aspect ratio as the golden ratio. Tunisia, Turkey, Tuvalu, United Kingdom, done that. United States. If anyone wants to actually draw this, good luck. Uzbekistan, Vietnam. And that's all the star flags we can do right now.
143 flags, 73% of the job done.
Okay, we're off to a good start. Before we move into the next chapter, now is the time to correct some of the mistakes I've made in the last video. Number 1, it is Thailand. I'm so stupid. Now I've learned how to say Thailand. I also learned this is Siam. And now to make atonement, I'm gonna learn how to say Thailand in the official language of Thailand.
ประเทศไทย ประเทศไทย
ประเทศไทย ประเทศไทย. Okay, I think that's the best I can do right now. For all the other mispronunciations of names I made, I'll try to learn all of them sometime later. Also, it shouldn't have been just Bahamas because the official name is The Bahamas. I entirely, completely, 100% blame Sporkle Admin for this mistake. So, hey, Sporkle Admin, here's how to say The Bahamas in the official language of the Bahamas.
The Bahamas.
Chapter 8. The Neverending Flag Gauntlet? What?
Welcome to the Neverending Flag Gauntlet. You will now select a flag and construct it, and then do that again and again for the entirety of this video. You will have to keep making creative ways to draw flags that only get harder and harder with that human brain.
What if I don't have that creative thinking?
Then you die.
Well, can I quit this challenge?
Now begin.
No.
Start now. You have 3 chances to fail.
Okay. I should start with something that I know I can construct. Let's do Libya. Last video we couldn't do it, but now we can. Plus, I wanted to talk about an important philosophy that will save us a lot of time later on. This is the construction sheet from Wikipedia. So right away we see a very complicated number, this length c. But where does that number come from? Well, here's what's actually going on. This star is facing left. To make that in Google Slides, you can rotate the star by 90 degrees. And what's the width of the star? According to the construction sheet, it's equal to the distance between the ends of the crescent.
Is that length constructible?
Yes, this is a 45-degree angle, so this is root 2 times the radius of the big circle, 3 root 2. Since the star is constructible, we can also construct its circumcircle by reversing the steps to draw an inscribed star. C is defined as the diameter of that, so that constructs C as well. This is the important part. Right now, I didn't actually calculate how to make this number from the numbers we know using the 4 operation symbols, but I visually showed you that I can actually make that circle. So this must be a constructible number because I can literally construct it. And then D is C multiplied by root 5 and something something, so D is also constructible. That means every number here on the flag is a constructible number. So the flag of Libya is constructible in Google Slides. Do you see how we are starting to make little bits of shortcuts? If we can just prove that every important number is constructible, that every important step in the construction is possible, then that fact alone is enough to let us mark the flag as complete and move on.
That is 1. Now pick another right away.
Okay, I think I'm gonna pick Turkmenistan, because I looked at the construction sheet, and while it looks really complex, everything in it seems to be rational. The carpet pattern to the left is not strictly defined, so we can quickly convince ourselves that it's doable. Let's zoom into the stars. Some key points are defined with coordinates, with the upper left corner of the green being 0, 0. We want to draw these stars, but to be able to draw a star, both its size and position need to be constructible. What's its size? It says the circumcircle's diameter is 48, constructible, so that's cleared. What's the position? One of the corners of the top star has integer coordinates, so this one's cleared. These stars are 64 apart, so the middle and bottom are cleared. One of the corners of the left star has integer coordinates, so that one's cleared. And the right one is the same distance apart from the center star as the left star, so if the center and left are constructible, the right should be constructible too. So that clears all the stars.
Okay, the hard part seems to be done, but what about the crescent? What's the size and position of the 2 big circles?
We should be able to calculate it. we know the 3 points it passes through. Calculating this by hand seems to be too much for me, so let's put that in a calculator. Equation of circle passing through the 3 points, and the radius...
The radius of the circle is the square root of 33,950...
Wait, there's no way. The stars are fine, but the crescent is what's holding us back?
Unless you know how to calculate square roots, that seems to be the case. So now you are down 1.
Oh, wow, this is not a good start. Okay, I need to pick something I know I can make. I believe North Macedonia in the last video was shown among the flags that require root 5 to make. So let's do that one.
Oh, right, that flag being there was a mistake.
What?
You see, sometimes the construction sheets are kind of misleading, and one of the sources for Macedonia on Wikipedia had a typo that we missed.
What? So it requires more than root 5?
Well, we don't know yet. You have to find the typo and construct the correct version. Who knows, maybe the correct version is easier.
Find the typo? How do I know something's wrong? Is it in that Macedonian language?
No, it's not. But there might not be enough information, so let's say the height and width of the flag are supposed to be 1 and 2.
Okay, then, here's 1/6, and presumably this is 1/6 too, so this would be 2 minus 1/3, so 5/3. Oh, this big rectangle's diagonal goes through this small rectangle, so they should be similar rectangles. The small rectangle says the aspect ratio is 3:4, I presume, but the big rectangle has height 1 and width 5/3. So that's the typo? It's 3:5 instead of 3:4?
Yes! Here is a clearer version of the construction sheet, and if we change the aspect ratio of the small rectangle to 5:3, then it becomes consistent with other construction sheets.
Okay, so this is the correct sheet.
Now let's try constructing it.
Okay, what's going on with these rays? Looks like we draw the triangles first and cover that with circles.
Can we draw the triangles? How wide and tall should they be?
Okay, the ones to the left and right, they're half as wide as the flag, so that's constructible, cleared. Okay, the top and bottom triangles, they're touching this circle, and the diameter of the circle is constructible, so their height must be constructible too, so yeah, that's cleared. The diagonal rays. What this sheet implies is that the tip of the diagonal rays should touch the corner of this rectangle. Using the aspect ratio of the rectangle, we can calculate how big it is. The circle has a diameter of 3/14, which is the diagonal of the rectangle, and we know 5 squared plus 3 squared is 34, so the width and height of the rectangle are respectively these numbers. Right, so we actually need root 34 to draw this flag, not root 5. That's bad news for me.
Unfortunately, that's another miss, so you have only 1 life now. In any case, this should be a good example that you really need to pay attention to every little detail in the construction sheet.
I think it's just an example that the creator of this video is stupid, but okay, whatever. Let's try Singapore, seems to be doable. All the numbers are rational, the crescent is doable, and the stars are aligned like a pentagon, which can be done by first a big circle, then an inscribed star, then centering 5 circles at each point of the star, and drawing 5 inscribed stars. Okay, so now we are back. Singapore is constructible.
Nice. Let's keep this pace.
Okay, let's move on right onto Cabo Verde.
Interesting.
Okay, my pronunciation is like
It's just sometimes you're going for the Portuguese or Spanish or French, and that's...
And the problem is I'm Korean. No, I'm fully cooked. I think it all started from that Côte d'Ivoire. I mean, if it was like Ivory Coast or like Cape Verde, then like maybe I might have been less wrong. Like it's Sporkle. All blame goes to Sporkle admin. Anyway, Cabo Verde. Hey, can you pronounce it better for me?
I am literally just you on a voice changer.
Whoa, just breaking the fourth wall? Moving on.
Cabo Verde.
The stars in this flag are aligned in a decagon, but we do have a 10-point star, so it's actually fine. Draw a big circle, then an inscribed 10-point star, and then just 10 circles and stars. It's the same for the flag of Dominica. Ambiguous drawing plus 10 stars arranged in a decagon.
Let us chime in for a bit. There's also a way to draw these without explicitly getting help from the 10-point star. A little exercise. Can you find a way to make a 10-point star without actually using the 10-point star? The solution is to use 2 pentagons or 5-point stars. We can rotate one by 180 degrees. Combine them, and they fit perfectly into one 10-point star. Back to you.
Okay, we have the flag of Venezuela. This flag is pretty unique. I don't think there is a clear construction sheet, so I don't know exactly what the angles of the stars are. If it is ambiguous and we are allowed to eyeball it a bit, then it becomes trivial, of course, as we mentioned in the previous video. I've seen one unofficial construction sheet that says we need to divide 144 degrees into 7 equal arcs, which would make this really complex, but the actual flag looks a bit different from this construction sheet too, so...
Well, that construction sheet is interesting, so we might return to it sometime again, but this does count as constructible.
Nice. For the next one, I select Honduras. This one is also interesting. The official sheet is very doable with our current knowledge, but Honduras also has an unofficial sheet.
Yes, while it's unofficial, just like Venezuela's, we left this one in because we think trying to make this one in Google Slides is worth it.
So it's gonna be like helpful for later? Okay. These stars look peculiar. It's slightly swelled up, defined with an outer diameter and an inner diameter.
And now we're gonna have another exercise, which is of course, can you draw this star in Google Slides? But beware, this exercise is much harder than any exercise we've done before. The solution is going to require multiple steps. If you couldn't fully solve it, you can pause the solution at any time. Here we go.
Here is the solution. Step 1. Make the 10 points that constitute this star. This is easy once you realize that degree-wise, these inner points are exactly in the middle of the outer points, which makes it very similar to constructing a decagon. We use one star for the outer points and one rotated star for the inner points. Step 2. We connect all the points with lines. Now, that does complete the shape of the star, but there's a final problem. An outline isn't enough. We need to color this if we want to draw a flag. This has to be a polygon, not just 10 lines. It's very intuitive to use the polygon tool here, but it doesn't work. It doesn't snap to the points we drew. Which means step 3. This is very painful, but we need to manually fill this shape only using right triangles and rectangles. It's trickier than all the previous uses of triangles, but it's nothing impossible. And that is mathematically a perfectly colored 5-point star defined with 2 diameters.
This exercise doesn't really matter for Honduras because this construction sheet was unofficial, but the flag of Papua New Guinea officially has these swelled up stars.
So Papua New Guinea is constructible thanks to that exercise. By the way, this bird, Rajiana bird of paradise, it looks complicated, but we can actually count this one as ambiguous. First of all, this number 34.5 seems to be an approximation. And all of these other numbers are just coordinates of specific points. So when we draw this, the only thing to be aware of is that rather than drawing the entire thing in one go, you should divide it into small shapes as we did in part 1, and make sure to snap the shapes at the very end to the correct coordinates.
150.
Nice! Okay, next let's do Azerbaijan with the 8-point star. There is an 8-point star shape in Google Slides, but I think we know by now that this shape is not enough. We need to draw 8 outer points and 8 inner points separately. Can we do the same thing as before? The amount we need to turn is half of 45 degrees, which is 22.5, so that's actually impossible with our 15-degree snaps. But luckily, Google Slides has a 16-point star, and that trivializes the problem. Here's how we draw the outline of the star. And after that, it's just another tedious coloring with right triangles.
Is it really possible to color that with right triangles? How can you know?
I mean, it's just possible every time. Okay, I'll do it just this once to show you that it's possible, but I'm not doing this again. Okay, next up, Nauru. This time it's a 12-point star. Again, we need one shape for outer points and one for inner points.
Here's another exercise. How do we draw that 12-point star?
So we have option 1, use 2 12-point stars and rotate one of them. Option 2, use 2 24-point stars. What's the answer? We needed 16-point stars to draw a proper 8-point star, so you'd think we need a 24-point star to draw a 12-point star, but it was a trick question! Option 1 works, because we can actually rotate a 12-point star by 15 degrees, and that aligns it perfectly for the inner points. So a mathematician would think the answer is both of them. But that was a trick too, so it was a trick question. Option 2 actually doesn't work in Google Slides because if you try to complete the star this way, you'll notice that you cannot actually snap to the endpoints of this star. For the 24-point star and the 32-point star, Google Slides doesn't actually let us snap lines into all endpoints, but only to the 4 basic directions. That basically renders the 24-point star useless. So option 1 was the only correct answer. Anyway, Nauru is constructible.
Very good. Also, reminder, you still have only one life.
Really didn't need that reminder, but okay, let's do Australia with the 7-point star. All the numbers in the construction sheet are rational, so that's fine, but we haven't drawn a 7-point star yet. So this time the problem is whether we can actually fit a 7-point star inside a circle, much like the case for inscribed 5-point stars. A 7-point star as wide as the circle will poke out of the circle. But let's try my magic trick again. Draw a square as tall as the star. Make the star as wide as the square. Bring it back and bam! It's magic! After that, we just do the rotation trick for the inner 7 points. And it's constructible. And the same trick would work for Jordan.
Wait, how long is this A?
This sheet tells us to calculate that by bisecting the angles of this triangle. In other words, it's the in-center of the triangle. By the angle bisector theorem, we know that the proportions of these two sides are equal to these two divided parts. And here, A to B happens to equal 1 to root 5. So luckily, the coordinates of the in-center can be constructed with just rational numbers and root 5.
154 flags complete.
Hey, this chapter is getting kinda long. Can we take a short break?
Chapter 9. No time to break.
That's not even a chapter name. Now you're just messing around.
We are noticeably getting slower, so let's do a bit of a review on what we achieved in terms of math.
Math? We used lots of new stars. They should give us something like how the 5-point star gave us root 5 and that weird number.
There's actually a better name for that weird number. The two lengths we've obtained from the star are the two side lengths of this right triangle, which has a hypotenuse of 1. This angle is 18 degrees, so the two lengths can be called sine of 18 degrees and cosine of 18 degrees, the latter being that weird number. The lengths we've obtained from other stars can be named similarly. Here's what we get from the 16-point star, the 12-point star, which unfortunately doesn't help because these two numbers were already constructible, and a 7-point star. Notably, these two are very complicated numbers that cannot be expressed by just square roots.
What in the world is that?
That is the actual number. These numbers are so complicated that actually, you cannot construct these numbers using just a straight edge and a compass. It is impossible to draw a 7-point star using a straight edge and a compass.
So we found something that Google Slides is better at compared to traditional mathematical tools?
Yes, for the first time, we are stepping outside of traditional mathematical construction.
That's honestly amazing.
Now let's get back to drawing flags. In fact, there aren't that many flags left with multiple pointed stars.
Well then, what should I do next?
We can give you some flags to do. Let's try Taiwan. It has a 12-point star not defined with 2 diameters, but defined like this.
Right. We can draw all those lines, so that already tells me that this is doable. And I think there's an easy way to do it, using some grouping and centering shenanigans. Like this. This is the first triangle. We can flip this to make the opposite side. Then we group them, copy it 6 times, rotate them, and put them back in the center.
Next up is Malaysia, or Malaysia.
A 1, 2, 3, 4, 5, 6, 7, 14-point star, defined with an outer and inner diameter.
This is another hard challenge. If you are still watching and holding up to this point, try this exercise. Can you draw a 14-point star if the 2 diameters are defined?
So we know that turning a 7-point star by 180 and combining gives us 14 points, but now we need to get angles in between these points. How? Well, look closer at Malaysia's flag. Doesn't this crease look like it's right on the middle? Yes, because the star is vertically symmetric. So the solution is to turn the 7-point star by 90 degrees. Then we get this beautiful construction.
Next up is Rwanda, a 24-point star with 2 diameters.
A 24-point star in Google Slides is again useless. But the 16-point star comes to the rescue this time because we can overlap 3 of them, rotate one by 15 degrees, and rotate another by 30 degrees. This results in a perfect 48-point star with snappable endpoints. And then it's just the same thing.
The next country is another hard to pronounce one.
Okay, let me try it. Timor-Leste.
Okay, let's go with that.
So this one's pretty weird because it is a 5-point star, but it's not upright. It points to the top left corner, and the rotation is not a snappable angle. The official description has a bit of an ambiguity, so here I have 2 versions of construction sheets. In the first version, the center of the star is positioned at the in-center of the black triangle. The distance from the left side is 9. In the second version, the center of the star is at the centroid of the black triangle. The distance from the left side is 8. The weird part is that right now, we can construct the first version, but we cannot construct the second version. And the only way I know of explaining why requires linear algebra. The first star is rotated this much, and that angle is the same as the angle in a right triangle with these lengths. 9 to 18, 1 to 2, similar triangles. And the second star is rotated this much. That angle is the same as the angle in this right triangle. Now, in linear algebra, there's a thing called a rotation matrix that I've touched upon for just a second in the last video. Basically, what it tells us is that if we can draw an upright star, and we can construct all the numbers in this right triangle, then we can manually draw the star rotated by that angle. There's a formula to calculate all the coordinates in the new shape. Currently, we know how to construct 1, 2, and root 5, but we don't know about root 97. So we can only construct the first version.
So this is like a half of a failure? So now you only have half of a life?
I guess. Like, what even happens if I'm out of lives? I'm not gonna actually die, am I?
Don't you remember the premise of this video? You draw 197 flags or die trying.
I said I never agreed to that.
Your next flag is Philippines. If you fail this one, prepare to get crushed as flat as a flag.
As flat as a... What does it even mean? Wait! When did the ceiling get this low?
Time is ticking.
Okay. Philippines? Right, give me the construction sheet. What is this monstrosity?
Let's see if you can make each part of the flag. Objective 1. The 3 stars representing the islands, defined with 2 diameters.
Okay, we've learned how to do that in Honduras.
That's not all. One of them is rotated 90 degrees, and the other 2, 30 degrees.
We just learned that that's possible too. All 3 sides of a right triangle with a 30-degree angle are constructible. That tells us that we can rotate any constructible point by 30 degrees.
Objective cleared. Now, to Objective 2, the sun.
That's obviously the problem. Let's first zoom in a little bit. The rays go out in 8 directions, and each part is further divided into 3 sections. The circle is really easy, so let's just focus on the rays. We also know that once we get the outline, it's easy to color the inside. So we should only care about getting the line segments correct. All of these lines going outward are defined to be rays that start from the center of the circle, and the angles between them are 1/96th of a circle. In our terms, it's like having to draw a 96-point star. The star with the most number of points that we managed to make up till now is a 48-point star, which is half of 96. And I don't have an easy way to double the number of points. So instead of trying to get 96 points on the circle, we will do something different. Imagine these 2 points are like the first 2 points of the 48-point star. We are going to construct their midpoint and connect it to the center of the circle. Constructing a midpoint is pretty easy. We need to draw a rectangle and halve its size. So once we do that, we can create this big middle ray. This top point is directly above the center of the circle with a distance of 19. And the next point is on this line that we just drew. It is the intersection of that line and this diagonal line going down from the top point.
How can we calculate that intersection?
There is a formula. So right now we know the 2 points on this one line and the 2 points on this other line. Let's say the coordinates of those 4 points are x1, y1 to x4, y4. We want to know the coordinates of this point, let's say px, py. This is the formula. I know it looks crazy, but this is a surefire way to get the coordinates of that point. If you look closely, the formula is just made of the numbers x1 to x4 and y1 to y4 and the 4 basic operations. So doing all those calculations is technically possible, and you know, my mission is just to prove that this is doable, not actually do it, so yeah. We know how to get this point, which means we know how to get this line, and this line as well. So this middle ray is cleared. Now to the small ray on the side. This time we prepare a 48-point star that fits inside a circle with a radius of 17. Suppose these are like the first 3 points of the star. This time we calculate the midpoint of the second and third point. And this time we need to calculate the intersection between this ray and this diagonal line. Again, using the same monstrosity of a formula. That lets us construct these 2 points, which in turn lets us construct all the lines in this triangle. And then of course we can flip the small right part to make the small left part, and we can rotate the bundle of 3 rays by 45 degrees to create all the 8 directions. And that is how you construct the flag of Philippines.
158 flags complete. Let's move on to the next flag.
The next flag,
What's wrong?
I don't know what else I can draw right now. I think most of the flags left require some kind of square root.
And you still haven't found how to make it?
Yes. If I just knew how to do that, I could probably clear like 30 more flags.
Well, we have to continue anyway. The next flag is South Korea.
No, that's one of them.
So you can't do it?
No.
Then you die.
No. Help!
I can't even see you anymore.
Wait, what's that? There's a crack in the...
Hey Zai, take this.
What the... What? How to draw square roots in PowerPoint? This does work. This is it. I can draw all of those flags. Wait, who are you? There are more rooms with other people. We need to work together. Cube roots, Bezier curves, sextic roots, septic roots.
20 flags left. 10 flags. 5 flags. 1 flag left.
Who is drawing a cat orchestra on our slide? Draw flags! Thank you so much for watching. Sorry for uploading late. There were multiple errors I found only toward the end of the production, and I had to redo lots of things. Thanks to all Patreon supporters. Thanks to everyone who submitted to the Math Clock contest that's going on right now until February 17th. Part 3 will be 100 times harder than Part 2, so stay tuned. Bye!